Hi friends, welcome to Megi Techie. Learn as engineer, teach as champion. First of all, I would like to thank my family for their continuous support and encouragement of creating these kinds of technical videos in public domain. And I would like to thank my mentor Professor R. Surendran from Government College of Technology, Coimbatore for igniting me a spark of creating these kinds of technical videos in public domain. And I would like to thank Almighty my God for my good health and broad mind. And I would like to thank my friends, followers, my dear students, and subscribers for their continuous support and encouragement. Today's topic of interest is types of fluid. Generally, we have six different types of fluids. One is ideal fluid, real fluid, Newtonian fluid, non-Newtonian fluid, ideal plastic fluid, and Thixotropic fluid. Let me explain another one in following slides. Before that, we are going to see a graph of mentioning different types of a fluid. So the graph is plotted between the velocity gradient and shear stress. The types of the fluid is very basically based on Newton's law of viscosity, that is tau is directly proportional to du by dy. According to the viscosity, the proportionality constant is found out using these graph. So here the x-axis carried out with the velocity gradient, that is du by dy, which is an independent variable, and shear stress tau in y-axis, it is a dependent variable. Why it is dependent? The shear stress is depends on the viscosity and the velocity gradient. That is why it is a dependent variable, and whereas the velocity gradient is an independent variable. So here I have plotted uh, x-axis as a velocity gradient and y-axis as a shear stress. Here the first type, an ideal fluid, it is in x-axis only. An ideal fluid is mentioned in x-axis, an ideal solid is mentioned in y-axis. So this is the basic difference between the ideal fluid and ideal plastic. And next is a Newtonian fluid. From this graph, we have clearly noticed that there is a linear relation between the shear stress and the rate of shear strain or velocity gradient for the Newtonian fluid, whereas for the non-Newtonian it is non-linear behavior. This you have to notice it. And next is a dilatant. Dilatant is also a one type of a non-Newtonian fluid where the exponential constant is there. And pseudoplastic. Pseudoplastic. And next is an ideal plastic fluid. It is nothing but a Bingham fluid. For your information, up to the certain load, it behaves as a solid. After that, it will have a linear relationship between the shear stress and the velocity gradient. So up to this region, if the load is removed, it can regain its position. Since it is a fluid, but it can regain its original position. That is why it is called as an ideal plastic fluid. So up to the yield, it can be as a solid. After that, it behaves like a linear relationship between the shear stress and velocity gradient. That is why it is indicated as an ideal plastic or Bingham fluids. Next is a Thixotropic fluid. It behaves like a non-linear relationship. After the yield point, it behaves like a non-linear relationship between the shear stress as well as the velocity gradient. So that is the basic difference between the ideal plastic as well as the Thixotropic fluid. So next I go with the what is the difference between the ideal fluid and the real fluid is. When ideal fluid, we can say it doesn't have any viscosity, there is no surface tension, it is incompressible in nature, it does not offer any resistance. Since it is having zero viscosity, so there is no shear stress, there is no resistance. It does not exist in nature. Ideal fluids are an imaginary fluids which is used for finding a basic relationship between two variables involved in fluids. So that is the idea about an ideal fluid. So it is an imaginary fluid. Okay. And the next is a real fluids. Real fluids, whatever the fluid we have seen in the real time, it is called as a real fluid. What all the fluids we are using, we are practicing, or we are experimenting, so that fluids are called as a real fluid. It have certain properties like viscosity, surface tension, compressibility, and so on. For an example, we can say an air is an real fluid, a water is a real fluid, glycerin is a real fluid, blood is a real fluid. Like that, we can say. In the next point, in certain amount of resistance is always offered. That is why it is real. All fluid in actual practice are all real fluids. Yes, it is. Next is a Newtonian fluid. We know that the Newtonian fluids, it is one type of a real fluid. All Newtonian fluids are a real fluid. There is a linear relationship between the shear stress as well as the velocity gradient. That is, the shear stress is proportional to velocity gradient. So we have noticed this equation. The shear stress is directly proportional to du by dy. Tau is directly proportional to du by dy. The proportionality constant is a viscosity. The real fluids like air, water, kerosene, glycerin, gasoline are all some of the examples of Newtonian fluids. And next is a non-Newtonian fluid. Yes, it is. It is also a real fluid. The shear stress is not proportional to velocity gradient, like the figure shown here. The some of the examples of non-Newtonian fluid, it is having a relationship between the shear stress and velocity gradient is non-linear. That is why the equation having the velocity gradient having mentioned with the power of n. So n is a constant. It varies with 0 to 1. Okay. For your information, blood is one type of a non-Newtonian fluid. Paint, it is one type of a non-Newtonian fluid. Slurry or concrete mixture, it is one type of a non-Newtonian fluid. Let me discuss. We know that so pseudoplastic and dilatants are one type of a non-Newtonian fluid. That is why it is following an equation. Tau is equal to mu into du by dy whole power n. If this n is greater than 1, it is called dilatant. If the n is greater than 1, it is called dilatant. If n is less than 1, it is called a pseudoplastic. The good example of a dilatant is a cheese or a mud. Mud is a dilatant. Where for the pseudoplastics, milk is a pseudoplastic fluid. A curd is a pseudoplastic fluid. So, I hope you have got a better information about the dilatant as well as the pseudoplastic. Next one is an ideal plastic fluid or Bingham fluids. So the Bingham fluids, in we know that in the graph we have that is certain a solid relationship. After that we have a linear relationship between the tau and the velocity gradient du by dy. So So certain up to this we have a constant, the stress of constant is being added. That is why the equation velocity viscosity equation and Newton's law of viscosity equation is added with some constant added with mu into du by dy, that is the shear stress. So here in a theory manner, the shear stress is more than the yield value, and thereafter the shear stress is directly proportional to velocity gradient, that is a linear relationship. For example, our toothpaste is one type of a Bingham fluid, and mud or a slurry is a one type of a Bingham fluid. And Thixotropic, there is a non-linear relationship. That is why a constant, a shear stress is equal to constant plus mu into du by dy the whole power n is coming to picture. The examples like lipsticks, enamel, printer ink, all are Thixotropic fluid. There, the shear stress is more than the yield value, and therefore the shear stress is not proportional to velocity gradient, that is non-linear relationship between the shear stress and velocity gradient after the yield value. So this is a Thixotropic fluid, and with this the types of fluids are coming to are completed. If you have any doubts, please let me know in the comment section. I will put another video for clarifying your doubts. If you like the video, please share and subscribe my channel Make It a Key with Santhosh, and you can get more and more videos on this channel in everyday manner. So thank you all.